Greetings and welcome to the problem set number 4 introduction for Chemistry 150, and I'm really glad to have you here. This is kind of a cool problem set in my opinion. It involves both the electrons around the atoms, how they're configured, as well as how electrons go around molecules to see the geometries, polarity, and stuff like that. So very, very powerful stuff when it comes to chemists and their arsenal of tools. This is not a video that you should watch from beginning to ending normally. What I would do is, of course, start the problem set on your own first, and then skip to the particular problem that I discuss so you can kind of get an idea what's going on. You don't have to watch the ones that you know already. That being said, if you have lots of questions on this, it's cool to watch it from beginning to ending. I'll do my best to keep it interesting for you. A periodic table should be used. Use the one at mhchem.org/pertab. It's a good one for all of us. If you have questions outside of this video, definitely feel free to contact me. Email is best, mike.russell@mhcc.edu. You can also talk to the LSC/Avid Center, which is located above the library on the Mount Hood campus, as well as at that address there, mhcc.edu/LSC. Okay, without further ado, let's get into the problem set and let's see if we can answer some of your questions. These first questions in this problem set will be all about Lewis structures and VSEPR geometry, and knowing how electrons are placed around molecules can be super helpful for chemists when they want to predict the reactivity of molecules, what they might do, what you might be able to use them for, and stuff like that. So the process will be very similar. For methane, the first one, which is CH4, first thing you want to do is count the valence number of electrons in the molecule. And to do that, you need a good periodic table. You look for the group number that both carbon and hydrogen are in this particular case. So if you look at the periodic table, carbon is group number 4, so it has 4 valence electrons. And hydrogen on the periodic table is in group 1A. The 1 is what we need here. So that means hydrogen has 1 valence electrons, but there are 4 of them. So I'll multiply that by 4. So 4 plus 1 times 4 gives 8 valence electrons, which would be the answer for the first part. But usually it's more helpful to divide that number by 2. There's going to be 4 pairs of electrons in this molecule, and we'll use those pairs in just a little bit. Now, to draw the Lewis structure, we need to find the central atom, and the central atom is usually the first atom listed in the molecule. This is definitely going to be carbon in this case, in CH4. Hydrogen can never be the central atom, so it will never be the central atom, and we'll talk about other ways to find sometimes central atoms later, but for right now, carbon is going to be the central atom. So I'm just going to draw the C, and I'm going to draw the other atoms all around it, which in this case would be 4 hydrogens. Now, right now, those hydrogens can drift away from the carbon with no problem unless I somehow tether them to the carbon. And so I'm going to create what's called a sigma bond or a single bond, depending on how you think about it, which is basically just a connection that keeps the hydrogens from floating away from the hydrogen. Now, each one of those lines I just drew is called a bonding pair. And you'll notice that earlier we had 4 pairs of electrons to place around. Well, each of those lines is a pair. It's a bonding pair. So I have at this point used up all of my pairs. I have no more pairs to make lone pairs, or as we'll see later, some double bonds and stuff like that. So this is the Lewis structure for CH4. Woohoo! It's just carbon with 4 single bonds around it, and you're good to go. So we got the valence electrons, we've got the Lewis structure. Now, electron pair geometry and molecular geometry, you'll need the table from the lab, or you can look this up online, either way. But what you want to do is you want to try and see how many clouds of electrons are around the central atom. And a cloud can be a lone pair or a bonding pair. Now, in this case, carbon has 1, 2, 3, 4 pairs of electrons around it. And though each one of those pairs is a cloud. So if you look at the table, when you have 4 clouds and all 4 clouds are connected to atoms, they're not lone pairs, then that means that the electron pair geometry is tetrahedral. You can write tetra for me, and I'm happy with it because I'm the instructor. I guess I should write the full tetrahedral. Anyway, just do as I say, not as I do. Anyway, the molecular geometry might be different if the central atom has a lone pair. But this particular example, carbon has only bonding pairs, so the molecular geometry is also tetrahedral. If you were to draw this out, the angles, which is the next part, each of those HCH angles would be about 109 degrees. Now, in a Lewis structure, you don't have any information on the geometry. So you can see if you're a geometry person, I've written HCH angles at 180, i.e. if they're directly across, or HCH angles at 90 degrees if they're to the right or the left. But in reality, this bond angle is important. They're actually more like 109 degrees. And on the next slide, I'll show you a better picture than your artistically disfavored instructor here is able to draw. But anyway, the true geometry would be more like a 109 degree angle, which is a tetrahedron. I'll show you a better picture of that here in a second. And then finally, molecule polar or nonpolar. Now, honestly, more molecules are polar than nonpolar, but if every atom is surrounded, central atom, is surrounded by the same kind of atom, i.e. this carbon is surrounded by just hydrogens, there's no chlorines or bromines or silicons or whatever, then that means this molecule is going to be non-polar. So again, most of the time you can honestly guess that the molecule is going to be polar, but this is an example where it is non-polar. Everything around that carbon is the same. You only have hydrogens. There's no bromines or chlorines or oxygens or whatever. So the answer's here. There's the Lewis structure. You don't have to draw the blue lines around it for the bonds like I did. 8 valence electrons, tetrahedral for both EPG and MG, bond angles 109, and nonpolar. Now, I promised you better pictures because I can't draw. So there is the Lewis structure for CH4, much more prominent. But you can see the central atom carbon has just hydrogens around it. Bonding pairs connect the hydrogen to the carbon, 8 valence electrons total. Electron pair geometry, when you have 4 pieces around the central atom, is going to be tetrahedral. No lone pairs, so the molecular geometry is also tetrahedral. Bond angles 109. It's a non-polar molecule. It's all symmetric and stuff like that. There's only that around it, so you're good to go. Now, I told you I would show you a 3-dimensional representation of the molecule, and this little thing at the upper right is actually a representation of methane, where the pink atom in the middle would be carbon, and the hydrogens are the white balls around it. And you can see that the angles are more 109. These things have 3-dimensional shape to them, which makes it both exciting and frustrating at the same time, as we'll see. But it is another level of complexity you just have to think about. But with these simple skills, you can find the Lewis structure for any problem, which is kind of cool. The next example is for nitrogen trichloride, and we're going to do all the same things that we did before. We're just going to go through them now with a different molecule. So first of all, count valence electrons. So nitrogen on the periodic table is group 5, so there's 5 valence electrons. Chlorine is in group 7, so there's 7 valence electrons, and there are 3 chlorines. So 5 plus 21 is going to be 26 valence electrons, and if you divide that by 2, that would be 13 pairs of electrons. So technically valence electrons would be 26, but we're going to use 13 here in a little bit. Now, Lewis structure. First atom listed, almost always the central atom, and definitely in this case, that's the case. Chlorine likes to be on the outside, we're going to see as we get further into this. But for right now, what I'm going to do is I'm just going to write nitrogen, and I'm going to put the chlorines around it. Now, you can put chlorines above, below, left, right, whatever you want. It doesn't matter. I put them on the left, right, and under it, but you could honestly do it in any direction. The Lewis structures, again, don't really have any information on the geometry. It's just trying to show you where the electrons are. Like before, you have to connect the outer atoms to the inner atoms. So I'm going to draw a sigma bond or a single bond between the chlorines and the nitrogens. That takes up 3 of my pairs. So I have 10 pairs of electrons to use now with the remaining molecule. Now with CH4, we didn't have any electrons left, so that was no big deal. But if you have lone pairs left, like we do, you put them on the outside atoms first, giving them an octet, and if you have any left over, you put them on the inside atoms. Now, chlorine, like most atoms, likes to have an octet. Octet means 8 electrons, but remembering we're dealing with pairs of electrons. So I'm going to put 3 pairs around that chlorine. And if you look then, chlorine has 1, 2, 3 lone pairs and a bonding pair. Now each lone pair is 2 electrons. Each bonding pair, the lines I drew, is also 2 electrons. So technically it's 2, 4, 6, 8 electrons around it. This gives chlorine an octet. And an octet is a measure of stability when it comes to chemistry. So this chlorine has an octet around it, and I use 3 more pairs. I have 7 pairs left to go. So I'm going to put octets on the outside atoms first, and if there's anything left over, we'll put it on the inside. So my remaining pairs, I'm going to give this chlorine an octet, which is 3 more pairs. I'm going to give the final chlorine an octet. And you can see now that I've used 6 more pairs. I have 1 pair of electrons left. And if there are any left over, they go on the central atom. You don't have to circle it like I did, but I often do as the instructor just to make sure it's more obvious. So this molecule has happy chlorines. Happy means octet, and chlorine has octets. They have 3 lone pairs and a bonding pair. That's happy. But the nitrogen is happy here too. Nitrogen also has an octet. It has 3 bonding pairs and 1 lone pair. That gives it an octet as well. So this is the Lewis structure for NCl3. Everything has an octet. Everything is cool. Now, hydrogen doesn't have to have an octet. Hydrogen only needs 1 bonding pair, and it's happy. It's a happy camper. But N and Cl in this molecule definitely need an octet. So this would be the Lewis structure for NCl3. Around the nitrogen, you have 3 bonding pairs. That's the lines right here, 1, 2, 3. And you also have 1 lone pair. So if you have 4 clouds around the central atom, that means then that the electron pair geometry is also going to be tetrahedral. So just like the CH4 example we looked at earlier, nitrogen here is also going to have a tetrahedral electron pair geometry. But the difference now between this structure and CH4 is that nitrogen has a lone pair on it. And a molecular geometry is what the molecule would look like if the lone pairs were invisible. Now, electrons are just shimmering things of energy, if they will, like waves. And you probably wouldn't see them, quote unquote, if you were down on the level of the molecule. But their presence would still be there. It would still push on the nitrogen and stuff like that. So if you look at that diagram from the lab or look this up online, the molecular geometry is called trigonal pyramid. Or pyramidal trigonal sometime, although I don't like that as much. Don't call it just pyramid. In later classes, there's another kind of pyramid, so don't just call it pyramid, but trigonal pyramid or something like that is fantastic. So that's the EPG and the MG. It's something you can honestly just look up in a table. Bond angles for anything tetrahedral will always be 109, and that includes this particular molecule too. Now, if you look this up on Google, you'll find that the lone pairs kind of squish those NCl bonds a little bit. So you might see numbers like 107 or something like that. That's fine if you want to put that down. Honestly, as long as you know it's about tetrahedral, that's what I'm totally happy with. We will talk more about lone pairs pushing down in the majors level class later. But for right now, if you put an answer which is close to 109, I am completely happy. And then finally, polar or nonpolar. In this molecule, not everything is the same around nitrogen. You have 3 Cls and 1 lone pair. And that lone pair is enough to make a difference here. So if everything is not the same around this molecule, that makes it polar. NCl3 definitely is polar. It's got an unequal distribution of electrons. If it was, say, NCl4 or something where the lone pair was removed and a Cl was put there, then it would be nonpolar. But that lone pair makes everything around the nitrogen not the same. It's asymmetric, so that means this molecule is going to be polar. Here's some better pictures instead of my kind of lame drawings. But anyway, you can see once again that you want to count up the nitrogen and 3 chlorines to get 26 valence electrons, or 13 pairs. The EPG, when you have 4 pieces, 4 clouds around nitrogen, would be tetrahedral. But because one of the clouds is a lone pair, it has a different molecular geometry name. It's called trigonal pyramid. The bond angles, though, are about 109, and because the lone pair breaks the symmetry of the molecule, that makes this a polar molecule. It's no longer a nonpolar one like CH4, but it does have some polarity. For our next example, we're going to look at carbon dioxide. Again, same kind of thing as before in the last 2 examples, just again with different pieces. So, good old carbon, if you look on the periodic table, carbon is in group 4A. It has 4 valence electrons. Oxygen is in group 6, and there are 2 of them. So if you count up the valence electrons here, you have 4 plus 12, 16 valence electrons, and if you divide that by 2, you have 8 pairs of electrons to put around. Cool. Now, Lewis structure, central atom, definitely the first one listed, carbon. Oxygens go on the outside. We need to connect the outer atoms to the inner atoms. I'll write 2 sigma bonds, or single bonds. That means I have 6 pairs of electrons left. Now, at the next step, you want to make those octets on the outside atoms first, and if there's any left over, you put them on the inside. So what we'll do here is we're going to give oxygen 1, 2, 3. That gives oxygen an octet, like it did the chlorine earlier. 4, 5, 6 gives that oxygen an octet as well. And now I'm out of electrons. Now at this point, you should check your molecule. Look for those octets. Remember, hydrogen doesn't need one, but basically everything else does, more or less. Now the oxygens are fine. They have 3 lone pairs and a carbon. And thanks for playing. The oxygens are fine. They have 3 lone pairs and a bonding pair. So 4 pairs total gives it an octet. But carbon only has 2 bonding pairs, and that's not going to make that happy at all. So if you have a central atom which doesn't have an octet, that's when you want to start making these multiple bonds. So what's going to happen here is one of these lone pairs is going to go away, and you're going to make a second bond to the oxygen. And I'm going to do it on both sides, because oxygen can still have 4 pairs. Like you can see here how in this version, oxygen has 2 lone pairs and now 2 bonds for 4 pairs and octet. But carbon now has 4 pairs as well. It has 2 blue and 2 red, if you will, for it. Now, the red bonds are technically called sigma bonds. It's the first bond that goes down. And the blue bonds here are technically pi bonds. So a sigma plus a pi bond makes a double bond, and that's what carbon and oxygen has in this case. They've got double bonds connecting them to give them an octet. Redrawn, the Lewis structure for carbon dioxide, in my bad handwriting of course, has a carbon in the middle, 2 double bonds connecting each of the oxygens, and the oxygens have 2 lone pairs. So that would be the Lewis structure for CO2. You don't have to put in different colors for the pi bonds and stuff like that. Now, electron pair geometry is going to be around the central atom carbon, and there are 2 double bonds around carbon. Now, here's the thing about double bonds and even triple bonds. They count as one big cloud. So carbon has one big cloud to the right, to that oxygen, and it has one big cloud to the left, to the other oxygen. And if there's 2 clouds, that means the electron pair geometry is linear. So this has a linear electron pair geometry. The carbon does not have any lone pairs on it, so the EPG and the MG, the electron pair geometry and molecular geometry, are both linear. All right, they're the same thing. You only have different names if there's a lone pair on the central atom. The bond angles for a linear geometry, 180 degrees. And polar, nonpolar, everything around the carbon is the same. You've got a double bond O to the right and a double bond O to the left. So this is considered a symmetric molecule, and this is a non-polar molecule. So CO2 is considered a non-polar molecule. Now, again, all my drawings are just horrible, so I apologize. Here's some better drawings and work done. You can see that the carbon in the middle has a double bond O on both the left and the right. This is what gives it the linear electron pair geometry and molecular geometry. Bond angles are 180, and it is nonpolar. It wants to be it's a symmetric molecule. The oxygens are as far apart from each other as they can be. This next example involves a compound called acetone. Acetone has a lot of uses in the real world. Acetone is an example of an organic molecule. Acetone is commonly used to remove fingernail polish from your nails, if that's something you do. Acetone can also be used as a solvent. It's great about taking out things that are more organic. We're going to draw the Lewis structure here for acetone, and we're going to use all the same rules. Now, one thing that is important here is that if you look at the structure, there's a C and a C and a C. And this is an example of where there's going to be a carbon oxygen in the middle and a CH3 on the left and a CH3 on the right. So think about that as we go through this molecule. However, the first step, you got to find the valence electrons. There are 1, 2, 3 carbons, which I've highlighted in red there, and each carbon has 4 valence electrons. Now, hydrogen, there are 3 on the left and 3 on the right. That means there are 6 hydrogens, and they have 1 valence electron. And there's also an oxygen, and oxygen has a total of 6 valence electrons. So you add all this up, you have 3 times 4, 12, plus 6, which is 18, plus 6, 24 valence electrons. And if you divide that by 2, you'll have 12 pairs of electrons. Drawing the Lewis structure for this molecule is a little bit different because there's so many atoms, but the structure itself is trying to give you an example of how it looks. So let's start by writing a carbon, 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 like that. Carbon is often the backbone of these molecules, and we're going to see this is very common. Now, the left-hand carbon is a CH3, and we've seen here how carbon likes to make single bonds to hydrogen because hydrogen can only handle single bonds to it. The right-hand side is also a CH3. So that takes care of the CH3 on the left and the CH3 on the right. Now you have to somehow connect those carbon atoms together. So I'm going to draw a single bond between them. And then finally, I need to put an oxygen somewhere. So let's put an oxygen right there. And you can see that even with this primitive structure, we have a CH3 on the left, a CH3 on the right, and a CO in the middle. I have only 12 pairs of electrons to deal with. So if you count up the number of single bonds I've drawn so far, there's 1, 2, 3 from the CH3 on the right, 4, 5, 6 around the central carbon, and then 7, 8, 9. I've used up 9 pairs so far, so I have 3 pairs left. And if you remember how this works, you would start by putting the lone pairs on the outer atoms first, i.e. oxygen, and if there are any left over, put them on the central atom, which would in this case would be the middle carbon. So I just put 3 lone pairs around. I have no more pairs, but my carbon is unhappy, the central carbon, because that central carbon only has 3 bonds. So like we did in the last example, I'm going to take off one of the lone pairs and make a double bond to oxygen right there. So this is the structure now, the Lewis structure for acetone. There's a CH3 on the left, a C double bond O in the middle, and a CH3 on the right. And you can see now why sometimes acetone is listed that way. The chemist is trying to give you like a hint as to what the molecule looks like. Next thing, describe the EPG and Mg for the central carbon. And again, that central carbon is this carbon right there. Okay, so electron pair geometry around that central carbon. That carbon has a single bond, a second single bond, and a double bond. Now, as we saw with the CO2 examples, doubles and triples count as one bond. So what that means here, there are 1, 2, 3 clouds around that central carbon. The double bond counts as just one cloud, and all 3 of them are connected to atoms. There's no lone pairs. So if you look on on the piece of paper from the lab, electron pair geometry is called trigonal planar. Planar triangle is used sometimes, but I prefer trigonal planar, to be honest. Don't call it planar, because there's another kind of planar we'll see in later classes. And don't call it trigonal, because there's actually a couple different kinds of trigonal available. If there are 3 clouds to atoms around a central atom, trigonal planar is the name you want to use. Now, there are no lone pairs, so EPG and MG will be the same. So this is also called trigonal planar for the molecular geometry. The bond angles around trigonal planar systems are 120 degrees, if you look on that same thing. And finally, around that central carbon, you don't have the same thing. Like you have a CH3 on the left, a CH3 on the right, and a double bond O on the top, if you will. And those are all not the same things. If they were all CH3s, we'd be symmetric. But this is not symmetric. A double bond O is different than CH3s. So we would call this molecule asymmetric, or better yet, it would be considered a polar molecule. And acetone is definitely polar. Okay, here's some better drawings and stuff that are better than your poor instructor's artistic skills. But anyway, you get the idea. 24 valence electrons, 12 pairs in the molecule. The molecule has a carbon-oxygen double bond in the middle with a CH3 on the left and the right, if you will. That gives it the trigonal planar electron pair geometry. It gives you a trigonal planar molecular geometry. No lone pairs around the central atom makes EPG and MG the same. Bond angles are 120 around trigonal planar systems, and this molecule is polar because you double bond O is different than the CH3s. It's going to be polar and be good to go. In this example, we're going to look at an ion. Now, an ion is just a chemical system that's either missing an electron or has extra electrons. In this particular case, we're looking at a cation. It's the ammonium cation. It's a positive ion. A cation is a positive ion. But to do all of these things, same process. So let's count valence electrons. Nitrogen is 5. Hydrogen is 1, and there's 4 of them. But here's the thing. Positive 1, which is what this thing is, means it's missing an electron. So I'm actually going to subtract an electron here. If it was a negative ion, like a -1, I would add an electron. But positive 1 means it's missing electrons, and that's what we're counting. So instead of 5 plus 4, 9 electrons, it has 5 plus 4 minus 1, 8 valence electrons, or if you divide that by 2, 4 pairs of electrons. All right, so positive means take away, and adding negative charges means add electrons. And that's a little counterintuitive sometimes when you're learning this, but it's just something to get used to. Okay, central atom must be nitrogen. It can never be hydrogen. So I'm going to put the hydrogens around the outside like that. I'm going to connect the outer atoms to the inner nitrogen with a sigma bond or a single bond. And you can see now I've drawn 4 lines. That's all of the pairs I have. So at this point, this is the Lewis structure for ammonium. Let's double check. Nitrogen has an octet. It has 1, 2, 3, 4 pairs around it, so it's happy. Hydrogen has just 1 pair, which makes it happy. So this is actually the Lewis structure for ammonium. Now, sometimes you'll see these things in square brackets like that with a positive charge. That's fine if you want to, or sometimes just a partial upper right-hand corner kind of thing, but that would be another alternative way to see this. So that's the Lewis structure. Now, electron pair geometry, pretty chill. The nitrogen, like the other ones we've seen, has 1, 2, 3, 4 clouds around it. All the clouds are connected to atoms. They're all the same kind of atom, too. So 4 clouds means the EPG is going to be tetrahedral. And molecular geometry is going to be the same. There are no lone pairs, so EPG and MG will be the same. They're both tetrahedral molecular geometry. Anytime you have tetrahedral, it's 109 degree angles like the other ones we've seen so far. And this molecule is symmetric. Everything around the central atom, the central nitrogen, is a hydrogen. So this is a symmetric molecule. Everything's the same. This is going to be non-polar. So for ammonium, you have a tetrahedral EPG and MG. The hydrogens are connected to the nitrogens. You can draw the positive charge in the corner if you'd like to. Angles are 109, like all the tetrahedrals, and it's nonpolar. Here's an example with some better pictures than the instructor can draw. And you can see once again that it's like 5 plus 4 minus 1, 8 valence electrons. Remember, take away for positive, add for negative. The nitrogen has 4 hydrogens around it, 4 clouds connected to atoms. That's going to be tetrahedral for both EPG and MG. Anytime you have tetrahedral, it's going to be 109 degree angles. And this molecule is nonpolar. It's symmetric. Everything around the nitrogen is the same, just a hydrogen. For question number 6, we're going to step back a little bit. We're going to look at the periodic table. And it says for each of the following sets of elements, choose the 2 that should have similar chemical properties. And a periodic table would be super helpful in this problem. In this problem, you want to look for 2 elements that are in the same column, the same up and down area on the periodic table, because elements in the same column usually have similar properties. So for example, on the first one, sodium and cesium, Na and Cs, are both group 1A metals. So we would expect those 2 to have similar properties. So again, we're going to look at the same group, the same vertical column on the periodic table, and definitely the first 2 are in group 1A. The other ones, it's a similar kind of thing. So for example, on the second one, germanium and tin, Ge and Sn, are both group 4A. Those would be the ones that should be similar. On C, strontium, Sr, and barium, Ba, are in the same group 2A, the alkaline earth, so they're similar. And the last one, the noble gases helium and neon, He and Ne, have similar properties. So if you go up and down in a group, you should find very similar properties amongst the elements. In this problem, we're trying to find the maximum number of electrons in a following subshells. And here we have 6p, 1s, 5f, and 4d. And if you've looked at this section, all of those are possible subshells where electrons can be held. Now, an orbital always holds 2 electrons. And every time you have a 6p subshell, the p is the important part. P subshells have 3 orbitals. And if there are 2 electrons per orbital, and there's 3 orbitals, you can probably imagine that 6p is going to have 6 electrons. And you can do a similar thing for the other ones. And I would focus on the letter here. P's always hold 6. So if it was 6p or 2p or 4p, it would hold 6 electrons. S's have 2 electrons. They have 1 orbital, so S's always hold 2 electrons. F will hold 14, and D will hold 10. So it really has nothing to do with the letter. Now, the letters do relate to the number, the value of L. And we're going to talk about this more in the 200 level. But if you're curious where these things come from, SPDF, that comes from L values of 0, 1, 2, and 3. So if you want to find the number of electrons, if this is more the way you like to roll, this equation right here, 2 times 2L plus 1 will tell it. So for example, on the P one I talked about earlier, you can see that P has an L of 1. So 2 times L, 2 times 1 plus 1 is 3, and 3 times 2, that's one way to see that you've got 6 electrons. And you can do that for S, you can do that for F, and D the same kind of way. This is a higher order kind of way. And we'll talk about this more in the 200 level. Stupid people drink fuel is a way that you can remember the order. Stupid is 0, that kind of counts. People is 1, drink 2, F is 3, etc. So this is one way to do it. But also, you can also just remember that P subshells hold 6 electrons, S subshell hold 2, F's hold 14, etc., etc. Lots of ways to do this in quantum chemistry, and the patterns will help you figure out what's happening. This question looks very similar, but notice that it's asking for the maximum number of electrons in an orbital. Now, 1s we saw earlier was 1 orbital, And P's, C down there, we saw had 3 orbitals. And we took the number of orbitals and we multiplied it by 2 to get the electrons. So remember that a subshell is like a dorm level of a dorm room, all right? And the number of rooms is like orbitals, but you can only have 2 electrons per orbital or two people per room. So the answer for the number of electrons in an orbital is just 2. Each one of them can hold only 2 electrons, all right? So this brings up a good point. Subshells are kind of like the levels of the dorm room, and some levels are fancier with more rooms, more orbitals or not. So subshells can have 1 orbital, 2 orbital, 3 orbitals, depends on the thing. S subshells have 1 orbital, P subshells have 3 orbitals, D subshells have 5 orbitals, etc., like that. So kind of think about this as we go through. An orbital is like a room in the floor of the house. It's different than the other ones. And thinking about this will help you to figure out what's going on. So there's number of electrons, there's number of orbitals, and all these different things inside. So just kind of do your best to figure it out. We're going to knock these out here. Some of the subshells are not allowed, and we can use a periodic table to answer this, or we can use an Aufbau. So if you followed the lectures, it was always starting with 1s, and then it went 2s, and 2p followed, and then there was 3s, 3p, 4s, 3d, etc. However, we never got to a 2d. There was a 4s. It snuck in before 3d, but there was never a 2D. So 2D would be an example of an orbital which is not allowed. And there's rules for that. It has to go with N and L, and we'll talk about it. But the easiest way is either just to figure it out in the periodic table if there's a 2D and there's not. The first D is 3D. Or you can use the Aufbau. Now this is an Aufbau diagram. It starts by having 1s and then 2s under it, 3, 4, 5, 6, etc. Then you go down by 1 and start P's, 2P, 3P, 4P, 5P. Then you go down by 1 and start D's, etc., etc. So notice that there is no 2D. Like 2D would be right there. That's not going to happen. There is a 4S, so that's allowed. There's also a 3P, so that's okay. But the F's you see don't start until 4. So there's no 3F or 2F. Those would all be disallowed combinations. So you can use an Aufbau to figure out which ones are not allowed. If it's not in that diagram, not going to happen. So I do recommend using an Aufbau diagram to do these kind of things. In this problem, we're going to write the complete electron configuration for each of the following neutral atoms. Now, neutral again means that the protons and the electrons are the same, and that'll be important for this kind of problem. So you can see on the first one, there's a lower left-hand corner 6 by the carbon. That helps us here because 6 technically is the atomic number, which is the number of protons. But in this problem, we need to know how many electrons a neutral atom of carbon has. And so that 6 also represents, for this problem, the number of electrons. So we're going to be dealing with a total of 6 electrons for carbon in A. We'll have 10 electrons for neon in B, etc., etc. And probably one of the best ways to handle this problem is to use the Aufbau diagram. And again, Aufbau diagrams can be so helpful. And again, it's kind of like a path. You start with the arrow there at the top at the 1s, and then you twist around and you go to 2s, twist around, go to 2p, then 3s, etc., etc. So that'll be the order in which we fill them in. And it's also important to remember that S always holds 2 electrons, while the P's hold 6 and D's hold 10. So in our first example there with carbon, with a total of 6 electrons, we're going to start at the 1s, and 1s will hold 2 of those 6 electrons, but then it's filled. And we have to go on then to the 2s orbital. 2s holds up to 2 electrons as well, so we'll have have 1s2, 2s2, representing the first 4 electrons. And then the 5th and the 6th electrons won't fit in the 2s, so we go to the next one, which is 2p. And 2p's hold up to 6. So we'll have 1s2, 2s2, 2p2 for our electron configuration for carbon. And if you're ever uncertain how this works, you can always follow the Aufbau diagram. Aufbau diagrams are really, really cool. And also, to double check yourself, all of those superscripts there in carbon, i.e. the 2, and the 2 right there, all of those numbers when added together should equal the atomic number, which again for carbon there is number 6. So 2 plus 2 plus 2 is equal to 6. I think we've done it good, and we're ready to go on to neon. For the next one, neon, we're going to start with the carbon configuration, and we essentially have 4 more electrons to put in. So 6 plus 4 is 10. That's where the 4 comes from. Now, remembering that P's can hold up to 6 electrons, we can put those additional electrons just in the 2p orbital. So neon would have 1s2, 2s2, 2p6. And again, check yourself. 1s2, 2s2, 2p6 has 2 plus 2 plus 6, 10 electrons. That's how many electrons we have to deal with, so we should be good to go. Now for phosphorus, we're going to go past the neon core, which is past 2p6. The next orbital to be filled in, if you follow the Aufbau, is the 3s. Follow those arrows. And again, like before, 3s's hold up to 2 electrons. So 10 plus 2, 12 electrons. We have 3 more for phosphorus to get to 15. The next one to be filled in is 3p. And again, p's can hold up to 6, but they can have less than 6. So we're going to write phosphorus as 1s2, 2s2, 2p6, 3s2, 3p3. And again, if you want to count all those electrons, it does go to 15, which is totally cool. You can kind of see how this works. Past phosphorus going to krypton, we're going to have a lot more electrons to fill in. But remembering here again that P's hold up to 6, S's hold 2, and D's hold 10, we can get 3p6 if we get up to 18 electrons. That's getting closer to 36. After 3p6, you go to 4s2. 4s's hold 2 electrons like the other s's. Then we go to 3d. Now this is the first time we've seen a d in this problem, but d's hold 10, so that would hold 3d10, and we're still just 6 short, so those last 6 electrons will go in the 4p orbital, so that would be 4p6. So all of this together would be 1s2, 2s2, 2p6, that's the neon core from before, 3s2, 3p6, that gets us to argon, and then finally 4s2, 3d10, 4p6 would be the electron configuration for krypton. Gallium has 5 less electrons than krypton. So you can think about it as going backwards a little bit on the Aufbau diagram. The 4p6 were the last electrons to get filled in by krypton. If we have 5 less electrons, you would still have a 4p1. So gallium is the same as krypton, it just has a 4p1 configuration instead of krypton's 4p6. And then finally, to get to cadmium, then we just keep on going. So you can see there that 4p6 is the last one to be filled in with krypton, and we have 12 more electrons to go on top of that. So 2 more electrons past 4p would be 5s. That would be 5s2. And then the next one in the little list there would be the 4d electrons. 4ds will hold up to 10, just like the 3d did. And if you count that up, that's going to give you the 48 electrons of cadmium. So it would be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10. Oh goodness. Anyway, you can see how the Aufbau diagram can be super helpful for filling in the electrons, and once the chemist knows where the electrons are, they can think about their reactivity and what they can do, stuff like that. So it's pretty cool for a chemist. Here's an electron configuration, and assuming these are neutral elements, let's figure out what atoms they are. And this actually isn't too bad. Earlier, I talked about how the superscripts are the electrons, and if you add them all up, like in this one there would be 6, you can quickly find out what element is, assuming they're neutral. So if it's neutral and there's 6 electrons, you can look for number 6 on the periodic table, and lo and behold, that's going to be carbon. And if you do the next one, 1 with 3s2, 3p3, you should see that that's a total of 15 electrons, and that's going to be phosphorus. The next one would be calcium, because it has 20 total electrons, and 3d6 on top of that would put you into the transition metals. That would be iron. So again, all you really have to do is count up the superscripts, find the total number of electrons, compare that to the number on the periodic table, and you've got your element, assuming it's neutral. Tell me on these examples if the atom is paramagnetic or diamagnetic. So we need an electron configuration here, first of all, but we're going to use orbital box a little bit more. If you have a single electron in an orbital that's up without a down or down without an up, that's going to make it paramagnetic. On the other hand, if every up electron has a down electron, it would be considered diamagnetic. Paramagnetic things are much more reactive than their diamagnetic versions, so it can be kind of an important consideration. Lithium has 3 electrons. That's a 1s2, 2s1. And in addition to that version, which is called spectroscopic notation, we're going to use orbital box notation. And we talked about this in the lecture a little bit. But anyway, lithium is 1s2, 2s1, and you can see on the right there, the 1s2 is in a box, and it's lower in energy, which is what it is, than the 2s1, and 2s is by itself. And since that 2s is all by itself, an up without a down, that's going to be, that's going to be the thing that makes this a paramagnetic atom. That up electron does not have a down, or the down does not have an up. It's better to write up first than down, but it's not a big deal. Now the bottom electrons, the up electron has a down, so that one would be considered diamagnetic. But the 2s, that electron by itself, that's going to make the whole atom paramagnetic. So we would call lithium a paramagnetic atom. Aluminum has a 1s2, 2s2, 2p6, 3s2, 3p1, or it has a noble gas configuration with a 3s2, 3p1 on top of it. And you can see there from that electron box notation, each of those boxes is an orbital. And we talked about how the p's have 3 orbitals for 6 electrons total. Aluminum has 1 electron there all by itself, and that's going to be enough to make aluminum paramagnetic as well. You only need a single electron by itself to make the whole thing paramagnetic. So again, for similar reasons then, aluminum, like lithium, is going to be a paramagnetic atom. Calcium has a total of 20 electrons. It's a 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. And everything except the 4s2 is argon, so that's why I kind of stopped there. But notice here how every up electron has a down. When you draw it out like that, even the 4s at the very end, the up has a down. So calcium is a diamagnetic metal, all right? It's going to be less reactive. So this is kind of what you have to do. Notice how the magnetism, the paramagnetic or diamagnetic, you always really look at the last orbital system. That's going to tell you if it's paramagnetic or diamagnetic, and that's kind of helpful too. And then the last one, bromine, which has just a gazillion electrons. All right, bromine is a shorthand notation. Argon, 4s2, 3d10, 4p5. And again, everything is going to be filled really except for that last set. And here's the 4p5. And if you look at it carefully, that last electron there is all by itself. Remember, you put 1 electron in per orbital first, and then you pair them up. But either way, you're going to have an odd electron. Bromine is a paramagnetic atom. So paramagnet means at least 1 up electron, 2 up electrons, or 3 up electrons are fine with no pairs. Diamagnetic means every up has a down. Ions can also have electron configurations. So the first 2 are negative anions, and the last 2 are positive cations. And on all of these, what you want to do is start with the neutral atom and then add electrons if it's a negative ion, or take away electrons if it's a positive cation. So as an example of this, sulfur is neutral, has 1s2, 2s2, 2p6, 3s2, 3p4. And remembering that P's can go up to 6, you can maybe see why sulfur likes to grab 2 extra electrons and become a 3p6. So sulfide is going to be 1s2, 2s2, 2p6, 3s2, and instead of having 3p4 in the neutral version, now you've got 3p6. And notice how phosphide, the next one, does the same thing. It was a 3s2, 3p3, and then it went 3p6 when it gained 3 more electrons. So both sulfide and phosphide have an argon electron configuration, that noble gas configuration. Now, the other ones do it too, but they're going to lose electrons. So beryllium was 1s2, 2s2 when it was neutral, taking away 2 electrons, takes away the 2s electrons. Beryllium 2 plus is 1s2, same electron configuration as helium. Sodium likes to be +1. Sodium neutral was 1s2, 2s2, 2p6, 3s1, 1 electron less to make it +1. It becomes a neon core. So those noble gases are the cool kids in the back of the school bus, and everybody wants to be like them. That's kind of what happens when it comes to the ions. Okay, that's it for problem set number 4. I hope this video has been helpful to you as you learn the material. If you do have further questions, reach out to me, mike.russell@mhcc.edu works best. You can also talk to the LSC/Avid Center, and they will help you as well. All right, good luck with your studying, and have a wonderful day.